Hello everyone, my name is Sarthake Choudhary and I will be presenting a paper on ImageNet classification with deep convolution neural networks, written by Alex Krzyzewski, Ilya Sutskever and Geoffrey E. Hinton. Through this paper, the authors highlight the use of a deep convolution neural network to classify 1.2 million high-resolution images in the ImageNet LSVRC 2010 contest into 1,000 different classes. On using a CNN model in this competition, they achieved top 1 to top 5 error rates of 37.5% and 17%, which was better than all the conventional ML algorithms used. So, what is ImageNet? It is a data set of over 15 million labeled high resolution images belonging to roughly 22,000 categories. It soon became a part of ImageNet large scale visual recognition challenge, providing a platform for all AI enthusiasts to use their classification models to get accurate results on a dataset as large as ImageNet. The competition uses a subset of ImageNet with approximately 1,000 images in 1,000 categories, with up to 1.2 million training images, around 50,000 validation images, and 1.5 lakh testing images. To achieve an accurate model for a complex object recognition task as this, authors have chosen CNN. So the question you must be having is, why CNN? Now, in a case like this, to learn about thousands of objects from millions of images, we need a model with a large learning capacity. The immense complexity of the object recognition task means that this problem cannot be specified even by a dataset as large as ImageNet. So our model should have lots of prior knowledge to compensate for all the data we don't have. The answer to all our problems is convolution neural networks. The capacity can be controlled by varying the depth and the breadth and make strong and correct assumptions about the nature of images, whether it's pixelated, occluded, or any other scenario. CNNs have much fewer connections and parameters, so they are easier to train, while the theoretically best performance is likely to be one slightly worse. So let me give you an overview of the model used. But before I speak, let me introduce this term named saturation of a network. Saturation refers to the state in which a neuron outputs values close to the asymptotic ends of the bounded activation function. That is, it cannot learn further or it is saturated. Saturation damages both the information capacity and the learning ability of a neural network. So now moving on to the model, the standard way to model a neuron's output f as a function of its input x is given by the equations as you can see in the slide. In terms of computation and training time with gradient descent, these saturating non-linearities I just mentioned are much slower than fx is equal to max of 0 or x. We refer to neurons with this non-linearity as rectified linear units. Deep convolution neural networks with rectified linear units train several times faster than the ones with tanh units. Let me demonstrate this with a statistical analysis done by the authors themselves. This analysis was done on CIFAR 10, a dataset which consists of 60,000 32 cross 32 color images in 10 classes, with 6,000 images per classes. The plot clearly shows the number of iterations required to reach 25% training error on the CIFAR 10 dataset for a particular four-layer convolution network. The plot clearly shows network with rectified linear units, which is represented by solid lines, reached a 25% training error rate on Cypher 10, 6 times faster than an equivalent network with tanh neurons, which is represented by dashed lines. This plot shows the reason why choosing CNN for such complex classifications is a good idea. So let me dive deeper into the rectified linear units with local response normalization. We know we know that all functions have domain, and many times we have to normalize the values we want to pass to a neural net in order to make sure it is in the domain of the function. Rectified linear units have the desirable property that they do not require input normalization to prevent them from saturating. If at least some training examples produce a positive input to a rectified linear unit, learning will happen in that neuron. However, we still find that the following local normalization scheme aids generalization, a key point in any neural network model. AI out here represents the activity of a neuron I, whereas BI represents the normalized activity. Through this equation, we see the sum runs over n adjacent kernel maps at the same spatial position, where n is the total number of kernels in the layer. Adjacent kernel maps are created due to a method named dropping, which I will be talking about later. Response normalization reduced their top 1 and top 5 error rates by 1.4% and 1.2% respectively. The effectiveness of this scheme was verified on the Cypher 10 dataset. CNN achieved a 13% test error rate without normalization and 11% with normalization. So now let's talk about implementation. How to implement such a system? It is definitely going to be computationally expensive, and a single GTX 580 GPU has only 3 GB of memory, which limits the maximum size of the network that can be trained on it. 1.2 million training examples for training networks are too big to fit on one GPU. Therefore, we spread the network across two GPUs. The parallelization schemes employed essentially puts half of the kernels or neurons on one GPU. The GPUs communicate only in certain layers. This means, for example, the kernels of layer 3 take input from all kernel maps in layer 2. Kernels in layer 4 take input only from those kernel maps in layer 3, which reside on the same GPU. Choosing the pattern of connectivity is a problem for cross validation, but this allows us to precisely tune the amount of communication until it is an acceptable fraction of the amount of computation. Let me give you an overview of the overall architecture. The network contains 8 layers with weights. The first 5 are convolutional and remaining 3 are fully connected. The output of the last fully connected layer is fed to a 1000-way softmax, which produces a distribution over the 1000 class labels. The softmax layer is the last layer based on the softmax function, which is a normalized exponential function or a generalization of a logistic function. All we are doing is simply passing the output of the last fully connected layer to a final output softmax layer that outputs the 1000 probability values of class membership. 1000 way is basically 1000 output classes or probability values or labels. The kernels or the neurons of the second, fourth, and fifth convolutional neural networks are connected only to those kernel maps in the previous layer, which reside on the same GPU, as shown in the figure. The kernels of the third convolutional layer are connected to all kernel maps in the second layer. The neurons in the fully connected layers are connected to all neurons in the previous layer. Response normalization layers follow the first and the second convolutional layer. The rectified linear unit, nonlinearity, is applied to the output of every convolutional and fully connected layer. Now, for successful classification, we need to tackle overfitting, a problem often seen in neural networks. Overfitting happens when one's model fits too well to the training set. It then becomes difficult for the model to generalize to new examples that were not in the training set. For example, a model recognizes specific images in the training set instead of the general patterns. The training accuracy will be higher than the accuracy of the validation or test set. We can reduce overfitting by adding more data, using data augmentation, which is again adding more data, use architectures that generalize well, add regularization, or reduce architecture complexity. Here we will talk about data augmentation and dropout method, which was implemented in this network model of this. So let's talk about data augmentation. The easiest and the most common method to reduce overfitting on image data is to artificially enlarge the dataset using label preserving transformations. Transformations can be any mathematical operations out here. Label preserving is used when dataset is limited. To overcome the possibility of overfitting, the training data is artificially augmented by adding replicas of training samples under certain type of transformation that preserve the class label. This improves the invariance and generalization of the network. Now there are two forms of augmentation. The first form of data augmentation consists of generating image translations and horizontal reflections. We do this by extracting random 224 into 224 patches from the 256 cross 256 images and training a network on these extracted patches. This increases the size of a training set by a factor of 2048, thus resulting the training examples are of course highly independent. The second form of data augmentation consists of altering the intensities of the RGB channels in training images. Specifically, we perform PCA on the set of RGB pixel values throughout the ImageNet training set. PCA is principal component analysis. It is used to reduce dimensionality of the feature vector while trying to retain as much information as possible. It is done by calculating eigenvalues and corresponding eigenvectors of a covariance matrix of the dataset. The dataset is then transformed with respect to the eigenvectors and the new dataset is generated. This way, we are able to create new pixel RGB, we are able to vary the RGB pixel values and generate new dataset, which is essentially data augmentation. To each training image, we add multiples of the found principal components with magnitudes proportional to the corresponding eigenvalues times a random variable drawn from a Gaussian with mean 0 and standard deviation 0.1. This was the method adopted by them. Now, another method of reducing overfitting is dropout. Now, in dropout, we combine the predictions of many different models, and it's proven to be very successful to reduce test errors. Dropout consists of setting to 0 the output of each hidden neuron with the probability 0.5. The neurons which are dropped out in this way do not contribute to the forward pass and do not participate in the back propagation as well. This way, every time an output is presented, the neural network samples a different architecture, with all these architectures sharing weights. The technique reduces complex co-adaptations of neurons since a neuron doesn't rely on the presence of other neurons, therefore learning more robust features. The models were trained using stochastic gradient descent with a batch size of 128 examples, momentum of 0.9, and a weight decay of 0.0005. This small amount of weight decay was important for the model to learn, and the update rule for the weight W is as shown in the slide. So, through this, the results in the LS VRC 2010 competition, the network achieved top 1 and top 5 test error rates of 37.5 and 17.0%, as it's clearly visible in the table. So that's all from my side. Thank you very much.